Welcome to Hart und Trocken. My name is Dirk Schiborn, and in this video I will explain to you what a derivative of a function is and how to calculate the derivative by calculating the slope of the tangent to this function. Differentiation and derivatives is all about the slope of curves. So let's start talking about the slope of curves. This is, for example, a polynomial curve of degree 4. We want to understand what the slope of this curve is at a given point A. Now, it is graphically obvious what we mean when we talk about the tangent of this curve at the point A. It is the straight line which goes through A and which is tangent to the curve at the point A. Now, let's say that if we speak about the slope of the curve at point A, we actually mean the slope of the tangent to the curve at point A. Now, if we change the position of the point A on the curve, the position and the slope of the tangent change accordingly. Now we recall what the slope of a straight line is. The slope of a straight line can be calculated by use of the slope triangle, which is this white triangle here. The slope triangle is a rectangular triangle where the hypotenuse is the line of which we want to determine the slope. One leg is parallel to the x-axis and the other leg is parallel to the y-axis. Then the slope of the line is defined as the quotient of this length by this length. In our case, 0.62 divided by 1, which is 0.62. It is handy to draw the triangle in that way that the leg parallel to the x-axis has length 1, because then we can directly read the slope here. Now again, if we change the position of the point A, the slope of the tangent changes accordingly. Now changing the position of the point A actually means changing the position of the x-coordinate of the point A. So the slope of the tangent of the blue curve is a function of the x-coordinate. That means the slope changes when the x-coordinate changes. That is a function. And we can use this insight to build a new function which gives us, for any x-coordinate, the slope of the tangent of the blue function. So we can think of the slope of the tangent to the blue function as a height over the x-axis, as this line indicates. So this line has the length 1.02 in this case. And again, if we change the position of the point A, or if we change the x-coordinate, the height of this line changes. And you can see how it draws a function. And we can plot the outline of that function. So what you see here, that new gray graph, is the function which gives us, for any point x, the slope of the blue function. This new gray function is called the derivative of the blue function. Now if we follow the slope of the blue curve in the different sections, we get insights regarding the shape of the derivative function. For instance, here in this area, the slope of the blue curve is negative. This is why the derivative function is below the x-axis. That means it's negative. Here in this area, the derivative function is positive. This is why the blue curve has positive slope, starting very, very slowly. This is why it's very close to 0 here, getting steeper and flattening again until it gets horizontal. And this is reflected by a falling slope until we have 0. Then the derivative dives below 0. This is why the blue curve goes down again. The slope goes down until it gets horizontal. This is where the derivative is 0. And then it starts increasing very quickly. And that coincides with the derivative getting very positive. Now let's summarize what we have learned. When studying a graph, we would like to have a precise measure of the steepness of the graph at a given point. This is given by the tangent at the point. The slope of the tangent to the graph at a point P is called the derivative of the graph at point P. Of course, a graph represents a function, so usually we don't speak of derivatives of graphs, but of derivatives of functions. So the derivative of a function f of x at the point x equals a is denoted by f prime of a. We can also say f dash of a. And we can determine the derivative of f of x at any point a, which means we can think of the derivative as another function. It is a function which is derived from f. This is where the name derivative comes from. Now suppose we are given just any function, like the blue function here, and it is our job to find the derivative of this function. That means to find that gray function, which gives us the slope of the blue function for any given x. Now, as we have understood, the way to do that is to find the slope of the tangent to the blue curve for any point a, or for any x. However, what I didn't tell you before is that it's not really easy to find that slope of the tangent. In fact, it is not easy to find the tangent itself either. By finding the tangent, I mean finding it in a mathematically precise way, and not just roughly graphically. Now, in fact, there is a very smart trick to find the tangent and the slope of the tangent, which actually has taken centuries for mathematicians to find, at least in the way we know it today. Let's try to understand this trick using a slightly simpler function. This is the function fx equals x squared, the normal parabola. Now we choose a value x equals a, at which we want to calculate the tangent to the function f. More precisely, we want to calculate the slope of the tangent to f, which goes through the point a, f of a. In this case, we have chosen the value 0.5 for a. Now the trick to construct and to calculate the slope of the tangent is initially not to construct the tangent, but to construct a so-called secant instead. In order to construct the secant, we need another point on the curve. We use the point at the position a plus h. That means the point which is the distance h further right on the curve. This point has the coordinates a plus h, f of a plus h. Now we construct the straight line through the points a, f of a and a plus h, f a plus h. That is the so-called secant going through these 2 points. The idea is that the secant is of course not the tangent, but it is some sort of approximation for that tangent. That approximation gets better when we decrease the distance h by which the second point is away from a. Let's try to animate this. You see how the point approaches the original point and how the secant approaches the tangent. Now the precise mathematical interpretation of the process of making h smaller is to replace h by a zero sequence which converges to 0. Consequently, we obtain a sequence of secants. For each member of that zero sequence, we get a corresponding secant. Now the next idea is to keep track of the slopes of that sequence of secants. So how do we calculate the slope to that secant? We do this by constructing a slope triangle to the secant. The horizontal leg has length h and the vertical leg has the length, well, it's fa plus h minus fa, because that is the difference of the y-coordinate of that point and the y-coordinate of this point, which is f of a. Now the slope of the secant is the quotient of the length of this leg divided by the length of this leg. That means the slope is f of a plus h minus f of a, which is this length, divided by h, which is this length. And in our example, we have a equals 0.5, and the length of h has been chosen to be 1. So if you replace a and h by 0.5 and 1, we get this expression. And if we evaluate this expression using the definition of f of x, which is x squared, we obtain the slope 2 for this secant. Now, as I said, the idea is to keep track of these slopes when we let h tend to 0. So we can animate this process by slowly decreasing h. Watch that h has been chosen to be 1 and h is going to be smaller in each step. So the distance between a and a plus h will decrease, the slope triangle will decrease and the secant will approach the tangent. Meanwhile, the slopes of the respective secants will also change, and we will see that quotient change. So let's start the animation. So you see how that quotient decreases and decreases, and the interesting thing is, where will this tend to? So that is a sequence, and our question is, what is the limit of this sequence? The limit of this sequence will be the slope of the tangent at A. Now we guess already where this goes to. Probably this will be 1. 5, 4, 3, 2, 1. And you see here in the limit, when h is 0, it can't calculate this quotient because there's a 0 in the denominator. This is exactly the reason for why we can't directly plug in 0 in this expression and simply calculate it. This doesn't work because we have 0 in the denominator. And that is why we have to choose the detour using the sequence of h's which approach 0 while the secants approach the tangent. But still, we have mixed feelings. There is no tangent, and there's a question mark, and there's a 0 in the denominator. So what has gone wrong in our procedure? What has gone wrong in our animation? The answer is, in the animation, h is decreased by a fixed amount in each step, finally reaching 0 after a finite amount of steps. Now replacing h by a 0 sequence instead, h will never reach 0. We can decrease h by as many steps as we want, it will never reach 0. Roughly speaking, it will reach 0 after infinitely many steps. So that is why we developed the technique of finding limits of sequences in our last videos. We need to apply this technique here in order to find the limit of that sequence of slopes. Now this said, let us fix the situation. First, I wipe out this formula and I will present to you a rather lengthy sequence of equations instead. Let's go through it step by step. Observe that this quotient is the slope of the secants, but now we have replaced h by a 0 sequence, indicated by h to 0, and we want to calculate the limit of this sequence when h tends to 0. In the first step, we simply replace f by the function which we have chosen for f, which is f of x equals x squared, so you see this square and this square, and we replace a by the value we have chosen for a, which is 0.5. 0.5. And now we start doing calculations as we know them from our video about limits of sequences. Here we simply expand this bracket by using the first binomial formula, which gives 0.5 squared plus h squared. And now we see that we can simplify because we have this expression minus, again, the same expression, which leads to this simplified fraction. And now it's very obvious that we can reduce by h, and that is the trick we need, because now we have 1 plus h divided by 1, knowing that h is a 0 sequence. Now applying the rules for limits, we know that we can directly let h go to 0. So we have 1 plus 0 over 1, which is 1. So that story of equations tells us that in the limit, the slope of the secants will be 1. And this justifies that we can draw a tangent at this point a, f of a, with a slope of 1. It is important to observe that the animation wasn't able to give us this result, even though it was obvious that the sequence of the slopes approached 1. But when the animation had reached h equals 0, we had a problem, because we couldn't calculate the final result. If h is replaced by a 0 sequence, well, then h in fact never reaches 0. And that is the good thing here. We can theoretically think about what happens if we walk along these infinitely many members of the sequence. And this approach indeed gives us the one we need. Now let us summarize what we have understood. We take a function like fx equals x squared and fix a point A. At this point A, we want to calculate the slope of the tangent, that means the derivative of f at A. However, we can't do that directly because we don't know the exact formula of that tangent. To resolve this situation, we instead construct the secant, which goes through AF and A, and another point on the curve, which lies h units further to the right than A. We then calculate the slope of the secant by using the slope triangle. Then we let h approach 0 by thinking of h being a zero sequence. Then our derivative is the limit of these slopes. In order to obtain this limit, we need to apply the theory of how to obtain limits of sequences. This is why we do this rather complicated calculation and obtain 1 in the limit. Well, now you probably think, what a hard and complicated procedure to find a simple derivative of a simple function at one point a, in this case a equals 0.5. And maybe you know already that the derivative of fx equals x squared is f prime x equals 2x. Well, at least that fits with what we have found, because if we plug 0.5 in here, we indeed obtain 1. But now be honest to yourself. How do you know that the derivative of x squared is 2x? Where do you know that from? It's just a rule. Maybe you know that you have to take down this exponent in front of the expression and decrease the exponent by 1. But where do you know that from? All these rules you might know about derivatives base on this idea with approaching the tangent by secants and doing calculations like these. In our next video, we will explore for simple functions like polynomials, trigonometric functions, and so on, how we can find rules for differentiation by applying this story. So that's it for this video. Thanks for watching and see you next time.